You think you know the sun. It rises. It sets. It keeps you alive. Scientists have studied it longer than any other star in the sky. And yet, real data coming from deep inside it keeps contradicting our best models. The flows are slower than they should be. The chemistry doesn't match the physics. A particle smaller than anything you can imagine is sending up signals we still haven't fully explained. We're going inside the star that powers all life on Earth, and what we find there will change how you see that bright light in the sky forever. If you enjoy what's coming, subscribe because this is only the start. Now, let's go. Every morning, the sun rises the same way it has for 4.5 billion years. Warm, steady, predictable. You've seen it so many times it barely registers. And that's exactly the problem. The sun looks so normal, so reliable, that most people assume scientists have it completely figured out. They don't. Right now, real data coming from inside the sun is contradicting some of the most trusted models in all of science. Measurements that took decades to collect, instruments launched into space at enormous cost, waves of sound moving through a ball of plasma 1,000,000 times the size of Earth. All of it is pointing at something that shouldn't be happening. The interior of the sun is behaving in ways that don't match what the equations say it should. This isn't a small correction at the edges. It goes straight to the core question of how the sun actually works, how it moves heat, how it builds magnetic fields, how it drives the storms that can knock out satellites, fry power grids, and endanger astronauts. The sun controls the space weather that wraps around our entire planet, and the engine running all of that sits hidden hundreds of thousands of miles below the surface, completely invisible to the naked eye. Here's what makes this so unsettling. The sun is the most studied star in the universe. By a huge margin, every other star is so far away that it looks like a pinprick of light, even through the world's most powerful telescopes. The sun is right here, close enough that we can track individual storms across its surface in real time. Scientists have been measuring it continuously for decades, and still, when they look at what's happening deep inside, the numbers keep coming back wrong. The mismatch showed up in the way plasma moves through the sun's outer layers. It showed up in the chemistry. It showed up in the particles streaming out of the core. Each time scientists refined their tools and looked closer, the gap between prediction and reality stayed stubbornly open. What's strange is that the standard picture of the sun works well for a lot of things. It explains the light we receive. It explains roughly how long the sun will live. It explains the general shape of the sunspot cycle that repeats every 11 years. But the moment scientists zoom in on the details, cracks appear, and the cracks are in exactly the places that matter most for understanding what the sun will do next. The history of science is full of cases where a small mismatch turned out to be a door to something enormous. A gap in the math becomes a new law of physics. A reading that doesn't fit becomes the discovery of a lifetime. The sun has already done this to scientists once before, in a way that rewrote the rulebook for particle physics entirely. Some researchers are quietly wondering if it's about to do it again. Before any of that can make sense, you need to understand how scientists actually see inside the sun at all, because they can't point a camera at it, they can't drill into it, they can't send a probe to the core and wait for a signal back. They do something far stranger, and it starts with sound. Picture the sun as a giant bell, struck from the inside constantly by the churning motion of plasma racing through its layers. Now picture scientists standing outside that bell, watching the surface vibrate, and working backward from every tiny shake and ripple to figure out exactly what's happening deep inside. That is helioseismology, and it is one of the most impressive scientific tools ever built. The idea sounds almost too simple. The sun has waves moving through it all the time. Hot plasma rises, cools, and falls. It crashes against other plasma coming up from below. These collisions generate pressure waves, the same kind of thing as sound waves in air, but moving through superheated ionized gas at speeds that would cross the entire United States in under a minute. Those waves travel through the sun's interior, bounce off the core, and return to the surface where satellites can detect the tiny ripples they leave behind. What makes this powerful is what those waves carry with them. Every time a wave passes through a region of the sun, it gets bent, slowed, or sped up depending on what that region is made of and how fast it's moving. By measuring millions of these waves simultaneously, scientists can build a picture of the interior, the same way a hospital ultrasound builds a picture of a baby before birth. The wave goes in, comes back changed, and the change tells you what it passed through. This technique gave scientists their first real map of the sun's inside. They could see how fast different layers were rotating. They could detect the boundary between the radiative zone and the convective zone. They could measure temperature and density at different depths without ever sending anything through the surface. For a while, it felt like the mystery was solved. The tool worked. The map was being drawn. Everything should have matched the models built over decades of theory. It didn't. When scientists used helioseismology to measure the actual flow speeds deep inside the sun's outer layer, they got readings far below what the simulations said should be there. The plasma was moving, but far more slowly than expected, not by a small margin. The gap was large enough that it couldn't be written off as measurement error. The Solar Dynamics Observatory, launched by NASA in 2010, made things sharper. It watched the sun continuously from space with no clouds, no night, no gaps in coverage. Day after day, year after year, it fed data back. Scientists processed that data and looked for the giant churning motions that every major solar simulation said should exist in the outer convective zone. The motions were there, but scaled down in a way that left researchers genuinely puzzled. What's key here is that helioseismology has been tested and confirmed in many ways. It's not a new or unproven idea. Scientists trust the technique. So when the technique says the interior is behaving differently than the model predicts, the problem belongs to the model. And that model covers far more than just the sun's internal temperature. It covers the entire engine that powers solar storms, magnetic cycles, and space weather. Something in that engine is off. And to understand what, you first need to know how the sun is actually built. Split the sun into 3 regions, and you get a picture that looks neat and logical on paper. A core at the center, where nuclear fusion runs. A middle zone where energy slowly crawls outward. An outer zone where plasma boils and churns toward the surface. Textbooks have taught this framework for decades. It's accurate enough to pass any exam. But one of those 3 layers is hiding something that keeps breaking the models. And it's the one closest to you. Start at the center. The core reaches about a quarter of the way from the sun's center to its surface. Inside it, hydrogen atoms are being crushed together into helium under gravity so intense that the pressure is roughly 250 billion times what you feel standing at sea level on Earth. That crushing produces energy, the same process, scaled up almost beyond imagining, that lights up the sky every day. The core is hot enough that a grain of its material dropped into the ocean would release enough energy to wipe out a city. Scientists understand the core reasonably well. The fusion happens, the energy comes out, the numbers mostly check out. The next layer is the radiative zone, stretching from the edge of the core out to roughly 2/3 of the way to the surface. Here, energy moves the way light moves through frosted glass. A photon, a particle of light, gets born in the core and starts crawling outward. Every few millimeters, it gets absorbed by a plasma particle, then spat out again in a random direction. It bounces and zigzags so many times that a single photon can take up to 100,000 years to cross this zone. The radiative zone is thick, dense, and slow. Scientists model it well enough, things mostly match. Then you hit the outer layer, the convective zone, and this is where the trouble lives. The convective zone is the outer third of the sun's interior. Energy can't creep through it the same slow photon by photon way anymore. The plasma here is less dense, and instead of passing energy along like a slow relay race, it moves it the way a boiling pot moves water. Hot plasma rises, cool plasma falls, rising and falling. over and over, in patterns that stretch from just below the visible surface all the way down through a layer roughly 130,000 miles deep. For scale, that's more than half the distance from Earth to the Moon, and it's made of plasma hotter than anything that has ever existed on our planet. This churning motion is called convection, and it matters enormously. Convection moves heat to the surface. It drives the flows that generate the sun's magnetic field. It sets up the conditions for sunspots, solar flares, and the storms that blast plasma into space at millions of miles per hour. Get convection right, and you understand the sun's magnetic engine. Get it wrong, and every prediction downstream falls apart. Scientists have built incredibly detailed simulations of this layer, powerful enough that running them required some of the largest supercomputers on the planet. Those simulations produce a convective zone that looks active, fast, and full of enormous rolling structures. The real sun keeps showing something quieter, and that gap between simulation and reality has a name. Close your eyes for a second. Picture a pot of water on a stove. The bottom heats up. Bubbles form. Hot water rises to the top, loses its heat to the air, cools down, sinks back to the bottom, over and over. Simple, familiar. Now scale that pot up to a sphere 100 times the diameter of Earth. Fill it with plasma hot enough to strip electrons off atoms, and run the heat source from inside instead of the bottom. That's the sun's convective zone, and it has been running that process non-stop for 4.5 billion years. The scale of this is almost impossible to hold in your head, so start with what you can see. On the surface of the sun, there are bright patches called granules. Each one looks like a slightly raised, glowing tile. The average granule is about the size of Texas. Across the entire solar surface, roughly 2 million of these granules exist at any given moment, constantly forming, rising, spreading out at the top, and sinking back down at the edges, each one completing its full cycle in about 10 minutes before disappearing and being replaced by a new one. Those granules are the visible tops of convective towers, hot plasma rising from below, spreading at the surface, cooling off, and falling back down along the edges. When you look at a photograph of the sun's surface and see that textured, almost pebbled appearance, you are looking at the tops of 2 million separate convective plumes, all running simultaneously, covering the entire face of the star. But the granules are just the surface expression of something far deeper and far larger. Below them, scientists believe there are larger structures called supergranules, each one roughly the size of the continental United States, which are themselves organized by even larger flows operating deep in the convective zone. Those deeper structures were the subject of one of the most important and most confusing measurements in recent solar science. Here's what the models said should be there. Large convective cells rolling through the deep interior, moving plasma across distances of hundreds of thousands of miles, generating strong flows that would show up clearly in heliosismic data. The cells were expected to be enormous. Some models put their scale at large enough to swallow the entire Earth dozens of times over, and they were expected to be moving fast. When scientists measured them, the speeds came back far lower than predicted, dramatically lower. The kind of lower that makes a scientist look at the equipment, check the calculations again, and then quietly start asking whether the model itself is wrong. This mismatch between the expected energy of deep solar convection and the actual measured energy became one of the central unsolved puzzles of modern solar physics. And the deeper scientists look, the stranger the picture gets, because convection doesn't just carry heat, it builds the sun's magnetic skeleton. And that skeleton is starting to look like it's been assembled by a process nobody fully understands yet. The surface of the sun looks almost alive. Under a high-powered solar telescope, it seethes and crawls, covered in a constantly shifting pattern of bright centers surrounded by darker edges. Scientists call these granules. Most people have never heard of them, but they are one of the most direct windows into how the sun actually moves its energy, and they are doing something remarkable every single minute of every single day. Each granule is a convective cell completing a full cycle. Hot plasma erupts upward at the center, travels outward across the surface at speeds approaching 1 mile per second, loses enough heat that it becomes cooler and denser than the material around it, and then falls back down along the darker borders between cells. The whole process, from birth to collapse, takes about 10 minutes. Then a new granule forms in nearly the same spot and starts again. Texas is an enormous state. Driving straight across it from east to west at highway speed takes close to 12 hours. The average granule is about that wide, 2 million of them covering the entire solar surface at once, constantly cycling, constantly transferring heat upward from the layers below. When you imagine all of them running simultaneously, you start to get a sense of just how much energy the sun is processing at every moment. But granules are only the smallest unit of this system. Group granules together, and they seem to organize into larger patterns called supergranules. A supergranule is roughly the width of the continental United States. It lives for about a day before dissolving, and its boundaries are where most of the sun's surface magnetic field gets swept and concentrated. Scientists detected supergranules decades ago, and the patterns are clear enough that researchers can track them across the solar disk in real time. Below supergranules, the models predict something even bigger: giant convection cells that operate in the deep interior, spanning distances that would dwarf anything visible on the surface. These structures have been theorized since the 1960s. Finding them, measuring them, and understanding their role would answer some of the most stubborn questions about how the sun's magnetic engine actually runs. That search went on for decades, and when scientists thought they finally found evidence of giant cells in the data from the Solar Dynamics Observatory, the discovery came with a problem attached. The cells existed, but the numbers surrounding them raised new questions rather than settling old ones. The speed was the issue. Giant cells were supposed to move fast. The heliosismic signal should have been strong enough to stand out clearly in the data. Instead, the measured velocities were far weaker than models predicted, so weak that some teams weren't even sure they were seeing the same thing at all. That uncertainty is what drove researchers toward a deeper look at the sun's rotation, because there is one thing about the sun's spin that is genuinely bizarre, something that solid objects simply cannot do, and it turns out this strange rotation pattern may be directly connected to why the convective flows keep coming back weaker than expected. The sun doesn't spin like a planet, and that difference might be the key to everything. In 2012, a team of researchers published a study that quietly sent a shockwave through solar physics. They had used helioseismology to measure the speed of large-scale plasma flows deep inside the sun's convective zone. The method was solid, the data was extensive, the result was genuinely alarming to anyone who understood what it meant. The deep convective flows were moving far more slowly than any major simulation had predicted. To understand why that's a problem, you need to know what those simulations were built to do. Solar scientists had spent years building computational models of the sun's interior. These models ran on supercomputers, used the best-known physics equations, and were designed to reproduce the observed behavior of the sun's surface and atmosphere. When they simulated the convective zone, they consistently produced vigorous, large-scale motions, big rolling cells of plasma churning through the interior, moving fast enough to generate clear signals that heliosismic tools should easily detect. The 2012 study looked for those signals. They ran their heliosismic analysis on years of data and measured the actual velocity of the large-scale flows. What they found was that the real sun's deep convection was moving at speeds roughly 1,000 times slower than the simulations said it should be. 1,000 times. That is the kind of gap that cannot be explained by small errors in the math. Something fundamental in the model was missing or wrong. This result became one of the sharpest edges of what scientists now call the convective conundrum. The word conundrum is doing a lot of work there. What it really means is this: the model and the measurement disagree so badly that at least one of them has to be fundamentally incorrect. and nobody is yet certain which one. One possibility is that helioseismology is somehow missing the signal. If the large-scale flows are structured in a way that helioseismic techniques are less sensitive to, the real velocities could be higher than measured. Some researchers have argued exactly this, proposing that the geometry of the flows makes them harder to detect than expected. That would mean the sun is actually moving faster inside than measured, and the problem shrinks. Another possibility is grimmer. The simulations themselves are missing key physics. Something in the real sun suppresses large-scale convection in ways that current models don't capture. If that's true, then the entire framework scientists use to understand the solar interior needs to be rebuilt from a different starting point. Either way, the stakes are enormous, because those deep flows are supposed to be the thing driving the sun's magnetic cycle, the sunspot cycle, the production of solar storms, the system that determines whether a giant eruption is about to blast a wall of plasma toward Earth at 4 million miles per hour. If the engine is being modeled wrong, every forecast built on top of that model is unreliable. And the more scientists dug into the data, the more they realized the convection problem wasn't standing alone. It was connected to something else entirely, something having to do with the way the sun spins. The convective conundrum has a simple description and a deeply uncomfortable set of implications. The sun's large-scale convection is behaving in a way that no standard model correctly predicted. The flows are there, but they're weaker than expected, organized differently than expected, and moving in patterns that keep resisting clean explanation. Start with what convection is supposed to do. In the sun's outer third, convection is the main engine that carries heat from deep inside up to the surface. Hot plasma rises, dumps its heat, cools, and falls. Sounds straightforward. But at large scales, in the deep interior, convection is also responsible for something more complex, creating the sun's magnetic field. The movement of electrically charged plasma through the sun's interior generates electric currents, and those currents generate magnetic fields. The whole system works like a dynamo, the same basic principle as a generator but operating inside a star. The flows feed the dynamo. The dynamo builds the magnetic field. The magnetic field organizes into sunspots, active regions, and eventually the eruptions that send solar storms toward Earth. So when the measured flows in the deep convective zone come back far weaker than the models say they should be, scientists aren't just seeing a small inconsistency. They're staring at a potential flaw in the foundation of every solar forecast ever made. Here's what makes the conundrum so stubborn. Both sides of the disagreement are hard to dismiss. The simulations are built on well-tested physics. Researchers have refined them for decades. They're not rough sketches. They're detailed, high-resolution computational models that reproduce many features of the real Sunday. When those models consistently produce strong, large-scale convection, it's worth taking seriously. At the same time, helioseismology is also a thoroughly tested tool. It successfully mapped the sun's rotation. It confirmed the existence of the tachocline layer. It has been cross-checked against other measurements in dozens of studies. When it reports that deep flows are weaker than expected, that's also worth taking seriously. So both the theory and the measurement are credible, and they disagree. That's the conundrum. Several possible explanations have been proposed. One is that the sun's rotation somehow suppresses the largest convective cells, squashing them into different shapes that helioseismology is less able to see. Another is that the convective zone contains narrow, fast-moving columns of plasma aligned with the rotation axis, structures that are too thin and too rotationally organized to look like the broad, rolling cells the models produce. A third possibility is that something happens at the boundary between the convective zone and the layer below it that acts like a brake on large-scale flow. None of these explanations has been confirmed. Some researchers think the conundrum is close to being solved. Others think the field is still missing something major. What everyone agrees on is this: the convective zone is where the sun's magnetic identity is forged. Get it wrong, and the downstream consequences reach all the way to Earth. Quiet convection means the magnetic dynamo runs differently than expected. A differently running dynamo means the sunspot cycle behaves in ways models can't yet reliably predict. An unpredicted sunspot cycle means surprises, and solar surprises have a habit of showing up in the worst possible ways. The next piece of this puzzle isn't about speed, it's about direction, about which parts of the sun spin faster than others, and why that tells us something the simulations missed. In March of 1989, a wall of plasma from the sun slammed into Earth's magnetic field and triggered the largest geomagnetic storm in recorded modern history. Within 90 seconds, the entire power grid of the Canadian province of Quebec collapsed. 6 million people lost power. It lasted 9 hours. Transformers were damaged as far south as New Jersey. The northern lights appeared as far down as Texas and Cuba, and this wasn't even close to the strongest storm the sun has ever produced. The storm that caused all of that started the same way every major solar storm starts. A region of twisted, concentrated magnetic field on the sun's surface became unstable and erupted. Billions of tons of plasma launched off the surface at millions of miles per hour and traveled the 93 million miles from the sun to Earth in less than 2 days. That magnetic field, the twisted, concentrated, unpredictable one, it comes from the convective zone. Here's the chain. Hot plasma rising and falling in the sun's outer layer carries electric charge with it. Moving electric charge generates magnetic fields, the same physics that runs every motor and generator ever built. In the sun, the scale is almost beyond comprehension. The convective zone acts like an enormous, constantly churning electromagnetic generator, and the magnetic fields it produces are the raw material for every solar storm that has ever hit Earth. Understanding convection means understanding where active regions form. An active region is a patch of the sun's surface where magnetic field lines have bunched together, twisted, and risen above the surface. These regions produce sunspots, flares, and the coronal mass ejections that can push walls of plasma toward Earth. Where they form, how strong they get, and when they erupt all depend on the magnetic field structure built by convection deep below. If the convective flows are being modeled wrong, then predictions about where active regions will form are unreliable. Predictions about how strong a given solar cycle will be are unreliable. And forecasts about whether a major eruption is coming toward Earth or pointing safely away from us become less trustworthy than they should be. The consequences of getting this wrong are growing. In the 1980s, the infrastructure vulnerable to solar storms was limited. Today, GPS satellites guide emergency vehicles, route aircraft, and underpin financial transactions worth trillions of dollars. Communication satellites that didn't exist 30 years ago now carry data that hospitals and military systems depend on. The International Space Station carries astronauts whose radiation exposure goes up sharply during major solar events. Power grids have expanded and become more interconnected, which makes them more efficient and also more vulnerable to geomagnetic disruption. A storm on the scale of the 1859 Carrington event, the largest solar storm in recorded history, hitting the modern world has been estimated to cause trillions of dollars in damage and potentially take months or years to fully repair. Scientists are not being alarmist when they say better solar models matter for civilization. They are describing a real risk with a real price tag, and that risk flows directly from the question of how the convective zone actually works. The answer to that question is tied up with something strange about the way the sun rotates, something that no solid planet can do, something that turns out to be central to everything. Spin a basketball, every part of it completes one full rotation in the same amount of time. That's because a basketball is a solid object, rigid, locked together. Every point on the surface travels at the speed the whole thing spins. The sun does something completely different. The sun's equator completes one full rotation in about 25 days. The poles take closer to 35 days. The same star, spinning at different rates depending on how far you are from its center line. This is called differential rotation, and while it's technically not surprising that a ball of plasma isn't rigid like a basketball, the consequences of this uneven spin reach deep into every open question about the sun's interior. To picture what this means, imagine painting a line from the sun's equator all the way up to the pole. Come back 2 weeks later, and that line is no longer straight. The equatorial end has moved forward while the polar end is lagging behind. The surface of the sun is being continuously stretched and twisted by its own uneven rotation. And that stretching is happening to magnetic field lines embedded in the plasma. Magnetic fields in the sun behave a bit like elastic bands buried inside the plasma. When the plasma moves, the field lines move with it. When the equatorial plasma laps the polar plasma again and again over months and years, it winds those field lines tighter and tighter, like twisting a rubber band around your finger. Eventually, wound-up bundles of magnetic field get strong enough to resist the convective flow, pushing against them. They push upward through the surface, and they emerge as sunspots. This winding process is central to the sun's 11-year activity cycle. It's the mechanism that converts the kinetic energy of rotation into stored magnetic energy that eventually erupts as flares and coronal mass ejections. And the rate at which it happens, the speed at which different latitudes pull ahead of others, depends directly on the interior flow structure in the convective zone. Here is where the problem bites. The observed differential rotation pattern at the surface is well established. Scientists have measured it many times in many ways. But accurately reproducing that pattern inside the star, through all the layers of the convective zone, requires the simulations to get the internal flows right. And the internal flows, as established in the previous chapters, don't match the measurements. In 2015, a NASA team, using Solar Dynamics Observatory data, reported evidence that large-scale flows, called meridional circulation, plasma moving from the equator toward the poles near the surface and back toward the equator deep inside, were slower and potentially structured differently than previous models assumed. Meridional circulation is one of the main drivers of the 11-year cycle. If it's different from what the models say, the timing and behavior of future solar cycles becomes much harder to predict. The surface is measurable, the interior is the mystery. And sitting right at the boundary between the parts scientists understand and the parts they don't is a razor-thin layer that might be running the entire magnetic engine. There is a boundary inside the sun that you will never see and can barely measure. It sits roughly 70% of the way from the center to the surface. It's only a few thousand miles thick compared to the 500,000 miles of the sun's radius. Most textbooks barely mention it. And yet, some solar physicists believe it is the most important location in the entire star for understanding how the sun's magnetic cycle works. It's called the tachocline, and it sits at the exact point where the sun's rigid interior ends and its differentially rotating outer layer begins. Below the tachocline, in the radiative zone, the sun rotates almost as a solid body. Every layer at that depth turns at roughly the same speed regardless of latitude. Above it, in the convective zone, differential rotation takes over, and the equator races ahead of the poles. That transition from uniform spin to uneven spin happens across a layer so thin, relative to the sun's total size, that it would be like a sheet of paper wrapped around a basketball. At this boundary, two different rotation rates are in constant contact. The mismatch creates shear. Think of two rivers moving at different speeds side by side. Where they meet, the faster water drags against the slower water, generating turbulence and swirling eddies at the boundary. Inside the sun, that shear zone acts on magnetized plasma, and the result is a region of intense electromagnetic activity. Many researchers believe the tachocline is where the solar magnetic dynamo actually does most of its work. The shear stretches and amplifies magnetic field lines, concentrating them into the strong bundles that will eventually rise through the convective zone, emerge at the surface, and form the active regions that produce sunspots and solar flares. If this picture is correct, then the tachocline is the manufacturing floor of the sun's magnetic output, and everything that erupts from the surface traces its origin back to this hidden, razor-thin zone. The trouble is that the tachocline is extremely difficult to study directly. Helioseismology can detect its existence and measure its approximate depth, but the detailed physics happening inside it, the exact nature of the shear flows, the way magnetic fields are stored and amplified there, and the precise role it plays in generating the 11-year cycle, remain active areas of research with significant gaps. Some models suggest the tachocline acts as a kind of reservoir, storing magnetic energy between solar cycles, building it up over years before releasing it as the next cycle ramps up. Others suggest the main dynamo action happens throughout the convective zone, with the tachocline playing a supporting role rather than the starring one. These are not small academic disagreements. They lead to fundamentally different predictions about how solar cycles will behave in the future. What everyone agrees on is that the transition from rigid rotation below to differential rotation above creates conditions found nowhere else in the Sunday. Conditions that make the tachocline the most electrically and magnetically intense internal boundary in the entire star. And just above it, in the full depth of the convective zone, scientists have been hunting for decades for something that should be enormous enough to see clearly, but keeps evading clean detection. Since the 1960s, solar physicists have been expecting to find enormous structures rolling through the sun's convective zone. The theory behind them is straightforward. Convection at small scales, the granules on the surface, is clearly visible. Convection at medium scales, supergranules, has been measured and mapped. The math strongly suggests that at the full depth of the convective zone, there should be convective structures operating at the very largest scale, cells so massive they would span hundreds of thousands of miles from top to bottom and wrap around a significant fraction of the solar circumference. These hypothetical structures are called giant cells, and finding them became one of the defining challenges of solar physics for more than half a century. To understand why they matter so much, consider what they would do if they exist and run at full predicted strength. Giant cells moving at the expected speeds would carry enormous amounts of angular momentum through the convective zone. They would redistribute the plasma in ways that shape the differential rotation pattern at the surface. They would influence how the sun's magnetic field gets transported from the deep interior up to where it emerges as sunspots. In short, giant cells would be a major part of the plumbing connecting the hidden interior to every visible feature of the sun's surface. For decades, the search came up empty. The helioseismic signal that should correspond to giant cells was at best marginal and at worst undetectable. Some researchers began to wonder if giant cells existed at all, or if the theory predicting them was missing something fundamental about how rotation and stratification at depth suppress large-scale convective motion. Then, in 2013, a team working with data from the Solar Dynamics Observatory announced that they had found evidence for giant convection cells. The announcement drew immediate attention. The team reported detecting large-scale flows consistent with the theoretical prediction, massive structures rolling beneath the solar surface, organized by the sun's rotation and potentially explaining why the solar equator spins faster than the poles. But the celebration was complicated. Other researchers looked at the same data or applied different analytical methods and reached different conclusions. The measured velocities associated with the proposed giant cells were far weaker than what most models predicted they should be. Some teams found evidence supporting the detection. Others argued the signal was too close to noise to be definitive. A genuine scientific controversy developed, and it has not been fully resolved. The situation illustrated something important about solar physics at this level of precision. Multiple teams studying the same star with the same observations can produce different results depending on the analytical choices they make, what spatial scales they target, and how they account for the competing signals in the data. The sun is not hiding its giant cells out of spite. Scientists are working at the very edge of what current measurement techniques can resolve. And just as the debate over giant cells was heating up, another piece of evidence arrived that made the whole picture more complicated. Scientists found that the very rotation of the Sun might be the reason why large-scale convection looks so different from what the models predicted. When NASA researchers announced in 2013 that they had found evidence of giant convection cells in the Sun using Solar Dynamics Observatory data, the solar physics community paid close attention. The finding was the culmination of a search that had lasted decades, and it carried real implications for some of the deepest arguments in the field. The team tracked large-scale plasma motions across the solar surface, using a technique that measures tiny Doppler shifts, the same effect that changes a siren's pitch as an ambulance passes you. By watching how plasma on the solar surface moved toward or away from the satellite, they could detect the enormous slow currents beneath. What they found looked like the giant cells theory had predicted: large, organized patterns of flow that wrapped around significant portions of the solar hemisphere and aligned with the direction of the Sun's rotation in the way theoretical models expected. The detection mattered because it connected the giant cells to differential rotation. The team proposed that these large convective structures were the mechanism through which the solar equator gets pushed to rotate faster than the poles. Each giant cell carries angular momentum as it rises and falls, and the statistical effect of all of them running simultaneously gradually builds up the equatorial speed excess that observers have measured at the surface for well over a century. But the problem started immediately when other teams looked at the numbers. The measured velocities of the proposed giant cells were far smaller than the models had predicted. The structures were real in the sense that something was there, but the signal was weak enough that researchers using different methods weren't always finding the same thing. Some helioseismic studies, targeting the same depth range, reported flows consistent with the NASA detection. Others, looking at slightly different scales, found weaker or differently organized structures. A few studies argued that the analytical method used in the original detection was more sensitive to some types of motions than others, which could make the measurement systematically miss part of the total velocity. This back and forth is normal in science. Discoveries get tested, methods get scrutinized, conclusions get refined. But what makes this particular argument unusual is its stake. Giant cells are supposed to be one of the main links between deep convective flows and the solar magnetic cycle. If they run at the velocities the original models predicted, they carry enough energy to matter enormously for the dynamo. If they run at the much lower velocities the observations suggest, the magnetic cycle has to be powered by something different, something that current models haven't captured. Neither option is comfortable. A weaker than expected giant cell structure means the existing model of how the Sun builds and sustains its magnetic field needs significant revision. A measurement problem means the tools currently used to probe the deep interior can't yet resolve one of the most important structures in the star. One explanation that gained traction after the detection was that the Sun's rotation is actively suppressing large convective cells. The physics of this is worth sitting with, because it changes the picture of what the convective zone actually looks like. And it raises a possibility that nobody in the field had fully anticipated before the measurements started coming in. Every magnet you have ever touched, every compass needle that has ever pointed north, operates because electrons are moving. Charge in motion generates a magnetic field. That's one of the most fundamental rules in physics. And the Sun runs the same rule at a scale that is almost impossible to take seriously. Inside the convective zone, billions of tons of electrically charged plasma are in constant motion, rising, falling, spinning, flowing from equator toward poles and back again, all of it driven by heat, gravity, and the Sun's rotation. Each moving blob of plasma carries charge with it, and all of that moving charge generates magnetic fields. The fields twist around each other, amplify through the shear at the tachocline, and gradually organize into the structured magnetic architecture that runs the Sun's 11-year activity cycle. This process is called the solar dynamo, Scientists have understood its basic outline for decades. What they have struggled to understand is the detailed mechanism, specifically where in the convective zone the dynamo does most of its work, how the magnetic field gets amplified from a weak background level to the intense concentrations that eventually push through the surface as sunspots, and how the entire cycle manages to reliably reverse its polarity and reset roughly every 11 years. The challenge is that the dynamo is powered by flows that can't be directly observed. The plasma in the deep convective zone is completely opaque to light. Helioseismology can probe it, but as the convective conundrum shows, the measurements don't always produce a clean picture. The simulations can model it, but the convective velocities in the models keep coming back stronger than the observations suggest. So, the dynamo is being modeled using flow inputs that may be significantly different from the real flows driving it. This creates a compounding problem. If the flow inputs are wrong, the dynamo output predictions are wrong. If the dynamo output predictions are wrong, then the model's forecasting where sunspots will form, how active a given solar cycle will be, and what kind of space weather Earth can expect are all built on a shaky foundation. There is also a timing mystery. The sun's magnetic field takes about 11 years to complete one cycle, flipping its north and south poles every cycle so that the full cycle from one polarity state back to the same state takes roughly 22 years. That timing is remarkably consistent across centuries of sunspot records. Yet the simulations of the dynamo, even the most detailed ones, struggle to reproduce it naturally from first principles. Getting the cycle length right typically requires tuning the model rather than deriving it directly from the physics of the flows. Some researchers believe the solution lies in the speed and structure of meridional circulation, the large-scale flow that carries plasma from the equator toward the poles near the surface and returns it toward the equator deep inside the star. Slower meridional circulation means the cycle takes longer. Faster means shorter. But the measured speeds of meridional circulation are uncertain enough that different research groups using different methods have published estimates that vary by a factor of 2 or 3. In other words, the clock that runs the solar cycle ticks at a rate that scientists can't yet measure precisely enough to predict the next cycle with confidence. And the explanation for why everything is this tangled might trace back to something as fundamental as what the sun is actually made of. Sunspots are dark patches on the sun's surface that appear when concentrated bundles of magnetic field push up through the photosphere and suppress the convection beneath them. They look dark because they are cooler than the surrounding plasma, often by nearly 2,000 degrees. They are also, paradoxically, the source of the most violent activity the sun produces. Flares and coronal mass ejections tend to originate from active regions centered on complex sunspot groups. The number of sunspots rises and falls on a roughly 11-year cycle that has been documented continuously since the 1700s. The modern numbering system goes back to the 1800s, and sunspot observations stretch back centuries before that. At solar minimum, the sun's disk can be nearly spot-free for weeks at a time. At solar maximum, dozens of active regions pepper the surface, and major eruptions happen multiple times per week. The cycle is one of the most reliable long-term patterns in solar science. And yet, predicting it accurately is still an unsolved problem. The challenge traces back directly to the convective zone and its hidden flows. The sunspot cycle is driven by the solar dynamo, which is powered by the differential rotation and the meridional circulation currents moving through the convective zone. Magnetic field is wound up by differential rotation, amplified by the shear at the tachocline, transported by meridional circulation, and eventually emerges at the surface as sunspots. The speed and structure of those internal currents determines how many sunspots form, how active the cycle is, and when it peaks. The problem is that the internal currents feeding this process are the same ones that helioseismology keeps measuring at speeds and scales that differ from what the simulations predict. Two research teams using different helioseismic methods have sometimes published contradictory measurements of meridional circulation speed at depth. One group found that the return flow deep in the convective zone was confined to a single fast stream. Another found evidence for multiple slower return flows stacked at different depths. If both can't be right, and they can't, then at least one team's measurement of the engine running the solar cycle is significantly off. Forecasting the next solar cycle is therefore less precise than it might appear from the outside. Panels of experts regularly publish official predictions for how strong each cycle will be. Cycle 25, the current one, was initially predicted to be average or weak. It came in stronger than expected. Cycle 24, before it was also forecast by some teams to be strong and turned out weaker than those predictions. The miss rate isn't embarrassing, but it's consistent enough that scientists are honest about the limits of what current models can do. Getting the internal flows right would change this. A precise measurement of meridional circulation, depth and speed, confirmed by multiple methods, would give dynamo models better input data and sharper forecasts. Sunspot cycle prediction would improve. Space weather planning would improve. Operators of satellites and power grids would have more reliable lead time. All of that depends on resolving what's happening in the convective zone. And before getting to the flows themselves, something surprising happened at the level of chemistry. Scientists tried to get more accurate about what the sun is actually made of, and in doing so, accidentally made the problem significantly worse. Around 2004, solar physicists thought they were making progress. A team of spectroscopists published revised estimates of the sun's surface composition. Using more sophisticated analysis of the sun's spectrum, the precise pattern of light and dark lines that tells scientists which elements are present and in what proportions, they updated the numbers for how much oxygen, carbon, nitrogen, and other elements the sun contained. The new estimates were considered more accurate than the previous ones. Better data, better models of the solar atmosphere, more careful analysis. And then the helioseismology results came back. Plugging the new composition estimates into the standard solar model made the model's predictions for the sun's interior sound speed profile significantly worse. Before the revision, the standard solar model matched helioseismic observations of the sun's interior sound speed to within 1% across most of the Sunday. After the revision, the match degraded. The region just below the convective zone, near the tachocline, showed discrepancies large enough to be a real problem. Two independent measurements, one of chemistry and one of interior physics, were pointing in opposite directions. This became known as the solar abundance problem. The word abundance refers to how much of each element is present. Getting the surface abundances more accurately, which is what the 2004 revision did, should have improved the solar model overall. Instead, it revealed or created a mismatch with the acoustic waves probing the interior. The reason this is so disruptive comes down to how solar models are built. A standard solar model starts with a composition and uses physics to calculate how the sun's interior should be structured, what temperature it should be at different depths, how dense the plasma should be, and how fast sound should travel through each layer. Helioseismology then checks those predictions against reality. If the composition input is wrong, the entire structure calculation is off. The pre-2004 composition values had been in use for decades and produced good agreement with helioseismology. The new, supposedly better values broke that agreement. Scientists were left with a troubling choice: accept that the newer composition measurements are correct and acknowledge that the standard solar model is missing important physics, or argue that the new spectroscopic analysis itself has systematic errors that need to be corrected. Both possibilities are being actively investigated. Some researchers have proposed that the mismatch can be fixed by adding physics that the standard model leaves out: extra mixing at the base of the convective zone, additional settling of heavy elements toward the core, or revised opacity values, meaning how strongly the solar interior absorbs radiation, could all potentially restore the agreement. Some of these fixes require adding processes that aren't directly measured and must be inferred, which makes them hard to confirm independently. Other researchers have re-examined the spectroscopic analysis itself and argued that the newer composition estimates may contain systematic errors introduced by the assumptions made about the Sun's outer atmosphere. A revised composition published in 2021 partially restored agreement with helioseismology. But the debate is ongoing. What isn't debated is what the solar abundance problem reveals. For even the most studied star in the universe, the most basic information, what it's made of, and how that composition matches its interior structure, remains unsettled enough to destabilize the models built on top of it. And the Sun has done something like this before. Once, a mismatch in solar data forced a rewrite not of astronomy, but of particle physics itself. The solar abundance problem is worth sitting with a little longer because the sequence of events that created it shows exactly how science at this level can go sideways in ways that feel counterintuitive. Here is the core of it. The Sun emits light across a huge range of wavelengths. Some of those wavelengths are absorbed by atoms in the Sun's outer atmosphere before the light reaches Earth. Each element absorbs specific wavelengths in its own unique pattern. By analyzing the pattern of missing wavelengths in sunlight, scientists can identify which elements are present in the Sun's outer layers and estimate how abundant each one is. This technique, called spectroscopy, is one of the most reliable tools in astrophysics. It works for the Sun and for stars thousands of light years away. For decades, the accepted composition of the Sun came from spectroscopic measurements made in the 1970s and 80s. Those values showed the Sun containing relatively high amounts of oxygen, carbon, and nitrogen compared to the surrounding interstellar medium. Solar models built on these values matched helioseismic measurements of the interior to within 1%. Scientists considered this strong validation of the overall picture. Then, a team in the early 2000s rebuilt the spectroscopic analysis from scratch. They used more detailed models of the Sun's outer atmosphere, accounting for the three-dimensional nature of the plasma motions near the surface, rather than treating the atmosphere as a simple, still layer. Their three-dimensional approach was considered an improvement. The new composition it produced showed lower abundances of oxygen, carbon, nitrogen, and other heavy elements than the older estimates. This was not a tiny change. Heavy elements affect how the solar interior handles radiation because they absorb more light than hydrogen and helium do. Their presence determines what physicists call opacity, the resistance the interior offers to outward flowing energy. Change the heavy element abundances significantly, and the opacity changes, and the calculated interior structure changes, and the predicted sound speed profile through the interior changes. The helioseismic data checks that sound speed profile. When the new, lower abundances were plugged into the solar model, the predicted sound speed near the base of the convective zone shifted away from the measured values by an amount that was immediately obvious and uncomfortable. Something that was consistent before the update became inconsistent after it. Researchers have proposed several ways out of this. One involves adding extra diffusion of heavy elements in the radiative zone, which would effectively mimic the effect of having higher initial abundances. Another involves revising the opacity tables used in the model, since the opacity values themselves carry uncertainties that might be large enough to absorb part of the discrepancy. A third involves arguing that neither set of spectroscopic measurements is fully correct, and that the true composition sits somewhere in between. Every proposed solution requires adding or changing something in the standard model that cannot currently be directly measured. That's not an unusual situation in physics, but it does mean that the solution, whatever it turns out to be, will need to be confirmed by multiple independent methods before it can be considered settled. The Sun's interior is speaking through helioseismology with remarkable precision. The surface is speaking through spectroscopy with its own precision, and the two are telling slightly different stories about the same star. Something is being lost in translation, and figuring out what it is goes to the heart of a question the Sun has already once used to overturn our understanding of the universe. Decades before the convective conundrum or the solar abundance problem, the Sun sent a warning that scientists almost missed. It arrived not as light, not as plasma, but as a particle so small and so reluctant to interact with anything that billions of them pass through your body every second without touching a single atom. Neutrinos. Neutrinos are born in the sun's core during nuclear fusion. Every time hydrogen is crushed into helium, neutrinos are released. They travel outward from the core at nearly the speed of light, pass through the entire body of the sun as if it isn't there, and stream out into space in every direction. A steady flood of them reaches Earth and passes straight through the planet as if it were made of empty space. In the 1960s, a physicist named Ray Davis designed an experiment to catch some of them. He built a detector at the bottom of a gold mine in South Dakota, 2/3 of a mile underground, deep enough that the rock above would filter out other particles that might interfere with the measurement. The detector was a tank containing 100,000 gallons of dry cleaning fluid. When a neutrino very occasionally interacted with a chlorine atom in that fluid, it would convert it into a radioactive argon atom that Davis could detect and count. By counting argon atoms, he could count neutrinos. The results, when they came in, were deeply uncomfortable. Davis was detecting roughly 1/3 the number of solar neutrinos that standard calculations said the sun should be producing. He checked the experiment, others checked his math. The answer kept coming back the same. The sun was producing far fewer detectable neutrinos than the models predicted, or so it seemed. This became known as the solar neutrino problem. For roughly 30 years, it was one of the most prominent unresolved tensions between theory and observation in all of physics. Several explanations were proposed. Maybe the sun's core was cooler than the model said, which would reduce fusion and produce fewer neutrinos. Maybe the standard solar model itself was wrong. Maybe Davis's detector was missing something. The actual solution, confirmed in the early 2000s, came from particle physics rather than solar physics. Neutrinos come in 3 types, called flavors. Davis's detector was sensitive only to one flavor, but neutrinos oscillate as they travel, shifting between flavors in a quantum process that was completely unknown when the original predictions were made. By the time solar neutrinos reached the detector, many of them had converted into flavors that Davis's experiment couldn't see. The sun was producing the right number all along. Physicists had simply not known that neutrinos could change identity mid-flight. This discovery earned a Nobel Prize, and it rewrote particle physics. A property of neutrinos that no one had suspected was confirmed by the mismatch between a solar model and an underground detector. The lesson is still reverberating through the field. Every time the sun's interior data disagrees with the model, scientists now have a specific historical reason to take the disagreement seriously. The last time they assumed the model was right and the data was the problem, the data turned out to be revealing a completely unknown law of nature. The convective conundrum is a different kind of mismatch, but it is a mismatch, and the question hanging over it is whether it's a small correction waiting to be made or something much larger waiting to be discovered. The sun's core is completely unreachable. No probe can survive the journey. No camera can see through 500,000 miles of plasma. The temperature at the center reaches about 27 million degrees Fahrenheit, and the pressure is so extreme that matter behaves in ways that have no equivalent anywhere on Earth. For most of human history, everything scientists believed about the solar core was inference, calculation, and educated guessing. Then neutrinos changed that. Every second, the sun's core fires roughly 236 trillion neutrinos into space. That number is so large it stops meaning anything unless you picture what's on the receiving end. About 65 billion of those neutrinos pass through every square inch of Earth's surface every second. Through the ground, through buildings, through you. Right now, as you listen to this, a constant flood of particles born inside the sun's nuclear furnace is passing through your body without touching a single atom. The fact that neutrinos barely interact with anything is exactly what makes them useful. Unlike light, which gets absorbed and re-emitted millions of times on its way out of the sun, taking up to 100,000 years to travel from the core to the surface, neutrinos escape in about 2 seconds. They carry direct information from the exact moment of fusion, completely unaltered by anything they pass through on the way out. A neutrino detected in a laboratory on Earth is a direct messenger from the sun's core, carrying news that is only 8 minutes old. Detecting them requires detectors of almost theatrical scale. The Super Kamiokande detector in Japan is a cylindrical tank buried deep underground and filled with 50,000 tons of ultra-pure water, lined with roughly 11,000 light sensors so sensitive they can detect a single photon. When a neutrino very occasionally interacts with a water molecule, it produces a faint flash of blue light that the sensors record. From those flashes, scientists can determine the energy and direction of the incoming neutrino, which tells them something about the fusion reaction that produced it. By measuring solar neutrino flux across different energy ranges, physicists can probe what the core is actually doing. The rates and energies of different neutrino types match specific fusion reactions. A higher rate of one type indicates more of one reaction happening. A lower rate indicates less. The neutrino data gives scientists a real-time readout of nuclear activity at the center of the sun, something helioseismology cannot reach on its own. Current neutrino measurements are broadly consistent with the standard solar model's predictions for the core. That is genuinely reassuring. The core, where fusion actually happens, appears to be working roughly as expected. The energy output matches. The fusion reaction rates are in the right range. The sun's central furnace is running on schedule. What that means for the convective conundrum is important. The problems in the sun's interior are concentrated in the convective zone, not the core. The fuel supply is fine. The energy generation is fine. What's uncertain is the plumbing that carries that energy upward and the magnetic engine built from those flows. Neutrinos confirmed that the core model is mostly right. The mismatch lives further out. And new solar detectors now being planned or built may eventually push neutrino measurements to a precision where even small deviations in core fusion rates could be detected. But there is one other thing the neutrino story confirmed beyond particle physics. It showed that when data and models disagree, the right response is to look harder, measure better, and resist the temptation to dismiss the discrepancy. That lesson shaped everything that came after. The resolution of the solar neutrino problem in the early 2000s was a landmark moment. Experiments in Canada, Japan, and the United States confirmed that neutrinos change flavor as they travel, which explained why earlier detectors were seeing too few. The full number of neutrinos the sun produces matched the model's prediction once all three flavors were counted together. Solar physics was vindicated. Particle physics gained a new fundamental discovery. Everyone celebrated and went home. Except the real lesson was more complicated than a clean vindication. The solar neutrino problem had lasted about 30 years from Ray Davis's first anomalous measurements to the confirmed resolution. During that time, the solar physics community was divided. Some researchers believed the problem lay with the standard solar model. If the sun's core was slightly cooler than calculated, it would produce fewer neutrinos, and the numbers would match without requiring any new particle physics. Some teams dedicated years to finding ways to reduce the predicted core temperature without violating other observations. They built increasingly sophisticated solar models, trying to make the discrepancy go away through astrophysics alone. They were wrong. The core temperature was fine. The model was not the problem. What this episode burned into the field was a specific kind of caution. When a measurement doesn't fit the model, the answer is almost never obvious, and the correct fix is almost never whichever explanation requires the least new physics. The neutrino case required genuinely new particle physics. The discrepancy was pointing at something real, and the real thing was something nobody had predicted. Solar physicists now approach the convective conundrum carrying that history. The measured flows in the deep convective zone are weaker than the simulations say they should be. The composition revision worsened the helioseismic fit. The giant cells came in slower than expected. 3 separate mismatches, each pointing at the same general region of the Sun, the convective zone, all accumulating over the past 2 decades. One response is to say the measurements are the problem. Helioseismology might be missing part of the signal. The spectroscopic analysis might carry systematic errors. The detection of giant cells might be affected by the analytical methods used. All of these are legitimate scientific possibilities that researchers are actively investigating. The other response, sharpened by the neutrino lesson, is to take the data seriously and ask what kind of physics could produce it. What would make the convective zone quieter than expected? What would suppress the large-scale flows? What would allow a composition change to degrade the interior model's performance so significantly? Some of the candidate answers are adjustments within the existing framework, better opacity tables, additional mixing, revised flow geometries. These could fix the discrepancy without requiring anything fundamentally new. But some researchers are asking whether the convective zone is doing something that current frameworks don't allow for, whether the rotation is shaping the convection in ways that existing simulations can't fully reproduce, whether the magnetic field itself is feeding back on the flows in a way that changes the entire picture. The neutrino problem turned out to be about nature, not about measurement error. It changed particle physics. The convective conundrum might turn out to be about measurement error, and the fix will be a recalibration, or it might turn out to be about nature, and the fix will be something much larger. What's becoming increasingly clear is that the answer depends on something the field has been wrestling with for years. The question of whether the Sun's own spin is actually fighting against its heat engine. For a long time, solar physicists thought of rotation and convection as 2 separate ingredients in the Sun's interior. Rotation shaped the large-scale flow patterns. Convection moved heat upward. They interacted, of course. But in most early models, they were treated as processes that could be understood somewhat independently before being combined. That assumption is now under serious pressure. The idea that emerged from the convective conundrum debate is that rotation may be actively suppressing the largest convective structures in the Sunday. The physics behind this goes by the name of the Coriolis effect, the same force that makes hurricanes spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. On Earth, the Coriolis effect shapes weather systems at large scales but doesn't prevent convection from happening inside a room or a pot of water. The Earth rotates slowly enough relative to the size of a typical convective cell that the effect is small. The Sun is a different situation. It rotates fast enough, and its convective cells are large enough that the Coriolis effect acts strongly on any convective structure bigger than a certain size. When a rising blob of plasma in the deep convective zone tries to grow into a large cell, the Sun's rotation deflects it. The upward motion gets twisted sideways. Instead of forming the broad, buoyant columns that simulations produce when rotation is turned off or reduced, the convection gets organized into narrower, more rotationally aligned structures. Some theoretical work suggests these rotationally constrained flows would look like columns aligned roughly parallel to the Sun's rotation axis. If the real deep convection has this columnar geometry, helioseismic techniques designed to look for broad, equatorially organized cells would find a weaker and differently structured signal than expected. The convective energy wouldn't have disappeared. It would just be organized in a geometry that the standard measurements are less sensitive to. This would explain part of the convective conundrum without requiring the Sun's convection to actually be weaker than the models say. It would mean the energy transport is happening, but through narrower, faster, rotationally shaped structures, rather than the slow, sprawling giant cells that simulations typically produce. The same total heat gets moved upward, the same total energy budget is satisfied, but the mechanism looks different from what was expected. If this picture is correct, then the models need to be rebuilt with rotation treated as a dominant constraint on convective geometry from the start, not as an add-on feature. The numerical challenge of doing this is significant. Simulating the full range of scales involved, from the granule-sized cells at the surface down to the hypothetical columnar structures in the deep interior, simultaneously and accurately pushes against the limits of even the fastest supercomputers currently operating. Several groups have published simulations that incorporate stronger rotational constraints and found that the resulting convective patterns look more consistent with helioseismic observations than older, less rotationally dominated models. Progress is real, but the models are still not reproducing every feature of the measured interior simultaneously. And a new question has opened up alongside this one. If rotation is shaping convection so strongly, then anything that changes the sun's rotation rate, its history of spinning faster when it was younger, for example, would have changed the convective structure and the dynamo it feeds. The sun's past rotation history might be written into its interior in ways scientists are only beginning to read. And sitting at the surface of all this buried structure is something strange and largely unexplained even after decades of observation: the corona. Picture a lava lamp. Blobs of wax rise from the bottom when they're hot, cool at the top, and sink back down. That is convection in its simplest form. Now imagine running that lava lamp inside a rapidly spinning container. The rising and falling blobs would no longer travel straight up and down. The spin would twist them sideways, turning what would have been simple vertical columns into curving, spiraling structures. That is approximately what some researchers now believe is happening inside the sun's convective zone. The specific prediction is that in the deep interior, where the influence of the sun's rotation is strongest relative to the driving force of heat, convection organizes itself into structures roughly aligned with the rotation axis. These are sometimes called banana cells or columnar structures, and they look very different from the broad, equatorially sprawling cells that older solar simulations produced. The key difference is orientation. Classic convection models produce cells that rise and fall in a pattern that tends to be oriented relative to the local gravity, meaning straight up toward the surface and straight down toward the center. Rotationally constrained convection produces cells that tilt or align with the axis the sun spins around, producing elongated columns that stretch from near the north rotational pole to near the south rotational pole, running through the deep interior like invisible pillars. These structures, if they exist at the scale and strength some models predict, would have a specific helioseismic signature that differs from the signature of equatorially organized giant cells. Some researchers have argued that certain features in the helioseismic data are more consistent with columnar convection than with the classic giant cell picture. Others remain unconvinced. The signal is subtle enough that different analytical methods, looking at the same data, can reach different conclusions. What makes this more than an abstract geometry debate is the downstream consequence for the magnetic dynamo. If the deep convective motions are columnar rather than broadly equatorial, the way they interact with the sun's differential rotation changes. The mechanism by which they transport angular momentum from the interior to the outer layers changes. The pattern of magnetic field generation at depth changes. And the character of the solar cycle that results from all of this changes in ways that wouldn't be predicted by older dynamo models. One of the testable predictions of the columnar convection picture is that the magnetic field generated at depth would tend to be organized differently from the field that older giant cell models predict. In particular, the timing of the solar cycle and the latitude at which sunspots first emerge at the start of a new cycle might behave differently under columnar versus classic convection. Researchers have been looking for these signatures in the long historical record of sunspot observations. The results so far are suggestive but not definitive. What's clear is that the geometry of solar convection is now a wide-open research question. The answer matters for the dynamo, the sunspot cycle, and the space weather that the cycle produces. But pinning it down requires measurements at a precision that current helioseismic tools approach but haven't yet fully achieved. And the difficulty of measuring the interior at this precision is itself a major part of the story. One of the most persistent frustrations in solar physics is that convection works beautifully in the models at small scales and keeps falling apart at large ones. At the granule scale, everything lines up. The simulations produce granules with the right size, the right lifetime, the right brightness contrast between the hot centers and the cooler edges. When you compare simulated images of the solar surface to actual photographs, they look remarkably similar. The small-scale convection physics is well understood. The equations handle it, the models reproduce it. Move up to supergranules and things get harder. Supergranules are well observed. Their size, their duration, the fact that magnetic field concentrates along their boundaries, all of this is established. But explaining why supergranules exist at the specific scale they do, rather than at a somewhat larger or smaller scale, remains an open theoretical question. There is no clean, universally accepted derivation of supergranule properties from first principles. They show up in observations. They partially show up in simulations. The full explanation for their scale is still being worked out. Move up to the giant cell scale, the full depth of the convective zone, and the trouble is most acute. Simulations, running with standard parameters, consistently produce strong, large-scale convective flows at this depth. The observations consistently suggest those flows are weaker and differently organized than the simulations say. The gap between the two doesn't close when you run better simulations with more computing power. If anything, more detailed simulations have sometimes made the disagreement clearer by producing even stronger large-scale flows than earlier, cruder models. The physics reason for this scale dependence comes down to what drives convection at different depths. Near the surface, the driving is strong and local. Heat piling up just below the visible surface produces vigorous convection that the models can simulate faithfully. Deep in the convective zone, the driving is weaker, the density is higher, and the influence of rotation is stronger relative to the buoyancy force pushing plasma upward. In this deep regime, a competition plays out between the heat trying to drive large-scale rising and sinking motions, and the rotation trying to break those motions into smaller, rotationally organized structures. The outcome of that competition determines whether you get broad giant cells or narrow columns, and the outcome depends on getting the balance between these forces exactly right in the model. Getting that balance right requires knowing the actual values of the relevant quantities at depth, including the convective velocities, the rotation rate at different depths, and the magnetic field strength. But those are precisely the quantities that are uncertain from measurements. The model inputs are uncertain. The model outputs then don't match the observations. And it's hard to know whether to fix the input uncertainties first or the model physics first. This circular problem has haunted the field for years. The most promising path forward involves improving the measurements enough to anchor the models more firmly, which requires better heliosysmic techniques, longer data records, and new approaches to separating different scales of convective motion in the data. Some of that is already underway. But the scale problem points at something broader than just solar convection. It raises a question that scientists hadn't fully anticipated when they started looking into the sun's interior with precision instruments. What happens when the same data is analyzed by two different teams using two different methods and they reach opposite conclusions? In 2012, a team published heliosysmic measurements showing that deep solar convection was moving far more slowly than expected. 4 years later, a different team published a study using a different heliosysmic technique on overlapping data and found results more consistent with stronger convective velocities. Both teams were credible. Both used established methods. Both had access to high-quality data from continuous space-based observations. They disagreed. This kind of situation is unusual in physics at the level of fundamental measurements. When two teams measure the speed of light or the charge of an electron using different methods, they get the same answer. That convergence is how scientists know those measurements are real. When two teams measure the same internal solar flow and get substantially different answers, something in the methodology is creating a systematic difference. The reason this happens in helioseismology comes down to the extreme subtlety of the signals involved. The surface of the sun is covered in noise, granule motions, oscillating waves, and magnetic activity. Buried somewhere in that noise are the faint imprints of deep convective flows. Extracting those imprints requires filtering the data, choosing which spatial scales to look at, deciding how long a time average to use, and making assumptions about what other signals might be contaminating the measurement. Different teams make different choices at each of these steps. Each choice is defensible based on established techniques. Each choice also selects for or against different types of signals. A technique optimized to detect broad, slowly moving structures will be sensitive to giant cells moving in a certain way. A technique optimized differently might be more sensitive to narrow, faster flows or to different depth ranges. If the real deep convection has an unusual geometry, one team's method might capture more of the signal while another team's method captures less. Both report a number. Both numbers are real measurements of something, but they aren't measuring exactly the same thing, and neither team realizes the difference until the theoretical framework for what the convection actually looks like is clear enough to resolve the ambiguity. This is one of the most frustrating aspects of the current situation. The path forward isn't simply to collect more data, though more data helps. It requires a better theoretical understanding of the flow geometry so that measurement techniques can be designed specifically to detect the right structures at the right scales. Theory and observation need to converge from both sides. Several collaborations are now underway specifically to address this problem. Researchers from different groups using different methods are comparing their results on the same data sets, tracking down exactly where and why their analyses diverge. The goal is to distinguish genuine geophysical signal from technique-dependent artifact. Progress is happening, but it's slow enough that in the meantime, there are open, published disagreements about basic facts of the solar interior. The speed of deep convective flows, the depth and strength of meridional circulation, the exact profile of the rotation rate at depth. These are all quantities where the published literature contains genuinely inconsistent results. And sitting above all of these unresolved interior questions is a feature of the Sun that is strange enough that it deserves its own chapter. A feature that has puzzled scientists for close to a century and that some researchers now believe may be connected to the hidden flows in the convective zone. Before space-based solar observatories, studying the Sun's interior had a fundamental problem. Ground-based telescopes could only observe the Sun during the day, and even then, clouds, atmospheric turbulence, and the rotation of the Earth constantly interrupted the measurements. Helioseismology requires tracking wave patterns continuously over long periods. A gap in the data breaks the analysis the same way a skipped beat breaks a rhythm you're trying to measure. The first major solution was the Global Oscillation Network Group, a worldwide network of ground-based telescopes positioned at longitudes spaced around the Earth, so that as one telescope lost the Sun at sunset, another was already watching from the other side of the planet. This network achieved near-continuous solar coverage, beginning in the 1990s, and transformed helioseismology from a promising technique into a precision tool. The next leap came in 2010, when NASA launched the Solar Dynamics Observatory into a geosynchronous orbit, a position from which it watches the Sun 24 hours a day without interruption. From that orbit, it photographs the Sun every 12 seconds across multiple wavelengths, transmitting roughly 1.5 terabytes of data back to Earth every day. There are no clouds, there is no night, there are no seasonal gaps, just continuous, uninterrupted solar observation at a resolution and cadence that no ground-based system could match. The value of continuous long-term data is that it lets scientists look for patterns that only appear over years or decades. The Sun's 11-year activity cycle is one example. Tracking how the interior flow structure changes across a full cycle requires data spanning at least a decade, ideally 2 or 3. Short observations catch snapshots. Long observations catch evolution. One of the most interesting findings from long baseline helioseismic studies is that the Sun's interior flows are not static. Meridional circulation, the large-scale flow that carries plasma from the equator toward the poles near the surface and back toward the equator deep inside, appears to change speed and possibly depth over the course of the solar cycle. At solar maximum, when sunspot activity peaks, the circulation patterns seem to shift relative to their behavior at solar minimum. This cycle dependence has real implications for dynamo models, since a meridional circulation that changes speed over the cycle would produce different magnetic flux transport at different phases. 40 years of accumulated data have also made it possible to study how the rotation rate at different depths varies with the solar cycle. There are slight but measurable changes in the rotation rate of the convective zone layers at different latitudes as the Sun moves between active and quiet phases. These torsional oscillations, as they're called, are subtle enough that they required long data baselines to detect clearly, and they carry information about where magnetic fields are concentrating inside the convective zone. The sheer volume of data now available is both an advantage and a challenge. Processing it requires sophisticated techniques, and the more researchers dig into it, the more features they find that need explanation. Some of those features are consistent with current models, some aren't, and some point to a phenomenon so counterintuitive that it has baffled solar physicists for nearly a century. The Sun's outer atmosphere is millions of degrees hotter than its surface, and some of the leading theories about why connect directly back to the hidden flows in the convective zone. Stand next to a campfire. The closer you get, the hotter it is. Move further away, and the heat drops. That's how heat from any source works. Energy spreads out with distance, and the further you go, the cooler things get. The Sun does the opposite. The visible surface of the Sun, the layer that produces the light you see, sits at roughly 10,000 degrees Fahrenheit. That's already hot enough to vaporize any material humans have ever produced. Now move outward from that surface, away from the energy source, up into the Sun's outer atmosphere, a region called the corona. The temperature doesn't drop, it climbs. And it climbs dramatically. Within a few hundred miles above the visible surface, the temperature reaches several million degrees. Some regions of the corona hit temperatures 10 or 20 times that. This is the coronal heating problem, and it has been one of the most enduring mysteries in solar science since the corona's extreme temperature was first measured in the 1940s. The basic thermodynamic expectation is violated. Energy should flow from hot to cold. The surface is cold relative to the corona. Something is depositing massive amounts of energy into the corona from below. And for decades, scientists argued about what that something was. There are two leading mechanisms. The first involves magnetic waves. When magnetic field lines rooted in the convective zone get jostled by the turbulent convective motions below, they can propagate wave energy upward into the corona, where the waves dissipate and deposit their energy as heat. The second involves magnetic reconnection. Convective flows at the surface constantly push and tangle the magnetic field lines rooted there. When tangled field lines from opposite directions are forced together, they snap and reconnect in a different configuration, releasing concentrated bursts of energy that heat the surrounding plasma. Both mechanisms are real, and both are observed operating in the corona. What remains uncertain is how much of the total heating each one provides, and exactly how efficiently convective energy at the surface gets converted into the wave energy or magnetic stress that eventually heats the corona. This is where the connection to the interior comes in. The waves and the magnetic stress that heat the corona are generated by the convective motions at the surface and the magnetic fields those motions produce. The strength, spectrum, and character of those waves depend directly on what the convection is doing. If the deep convective flows are structured differently from what models say, the magnetic field they produce will be structured differently, and the heating input to the corona will differ from what current models predict. Better models of the convective zone, with more accurate flow geometries and velocities, would improve models of how coronal heating works. The corona is not isolated from the interior, it is the downstream product of everything happening in the layers below. And the corona doesn't just sit there glowing, it produces the plasma streams and explosive eruptions that drive space weather. which brings everything back to the question of what happens to Earth when the sun's hidden engine misfires. That question has real and growing consequences for the world humans have built. On September 1st, 1859, an English astronomer named Richard Carrington was sketching sunspots through his telescope when he witnessed something no scientist had ever recorded. An intense white light erupted from the solar surface, flared brilliantly for about 5 minutes, and disappeared. Carrington noted the time. About 17 hours later, the largest geomagnetic storm in recorded history hit Earth. Telegraph systems across North America and Europe failed. Operators reported receiving electric shocks from their equipment. In some areas, telegraph lines that had been disconnected from their power sources continued to transmit messages purely on the current induced by the geomagnetic disturbance. The northern lights were visible as far south as the Caribbean. Papers reported that Hawaiians could read outdoors at midnight by the light of the aurora. That event, now called the Carrington event, was caused by a coronal mass ejection, an eruption in which billions of tons of magnetized plasma from the corona are launched off the sun at speeds reaching several million miles per hour. The plasma plows into Earth's magnetic field, compressing it on the sunward side, and drives intense electric currents through the upper atmosphere and the ground below. Coronal mass ejections originate in active regions. Active regions are patches of the solar surface where magnetic field lines have become concentrated, tangled, and stressed. The stress builds until the field configuration becomes unstable, and then it erupts, sometimes hurling a coronal mass ejection into space. The direction matters enormously. Most eruptions miss Earth. The ones aimed directly at us are the ones that cause geomagnetic storms. Every step of this process traces back to the convective zone. Active regions form where magnetic field generated in the interior rises through the surface. The strength and complexity of that field depends on how the dynamo built it, which depends on the convective flows feeding the dynamo. Whether an active region erupts in a relatively simple flare or a massive coronal mass ejection depends on the geometry of the field, which depends on how it was transported through the convective zone before emerging. Models that get the convective zone wrong produce active regions with the wrong properties. They form in the wrong locations, carry the wrong amount of flux, and interact with neighboring regions in ways that differ from what actually happens. The space weather forecast built on top of those models carries those errors forward. Currently, forecasting a major coronal mass ejection more than about 1 to 2 days in advance with meaningful accuracy is beyond what any operational model can do. The fundamental limit is the difficulty of predicting when and where the magnetic field will reach the threshold for eruption. Improving that forecast requires improving the model of how the magnetic field gets built and transported, which requires improving the model of convective flows in the interior. The science is not there yet, but the stakes are enormous enough that multiple space agencies, research institutions, and government bodies are actively working to close the gap. The effort has pushed scientists to think more ambitiously about the computational tools they use to model the Sunday. And what they're finding is that even the most powerful computing systems on Earth are barely sufficient for the task. The world's fastest supercomputers are machines that would have seemed like pure science fiction a generation ago. They occupy entire buildings. They consume as much electricity as small cities. They perform calculations at speeds measured in quintillions of operations per second. And when scientists point them at the problem of simulating the sun's convective zone at full physical detail, the computers run for months and still can't capture everything that matters. The core difficulty is called the range of scales problem. Inside the sun's convective zone, physically important processes happen simultaneously at vastly different sizes. Granules on the surface are roughly 1,000 miles across. The convective zone itself is about 130,000 miles deep. That's a factor of roughly 130 in spatial scale between the smallest convectively relevant structures and the largest. Simulating both simultaneously, with a grid fine enough to resolve the small features and large enough to contain the big ones, requires a number of grid points that exceeds what even modern supercomputers can handle. Researchers deal with this by making trade-offs. A simulation targeting small-scale surface convection uses a fine grid over a small volume. A simulation targeting global-scale flows uses a coarser grid over the full sphere. Neither can capture everything. The results from each must be compared and combined carefully because the two regimes interact. Small-scale turbulence affects large-scale flows through a process called transport of angular momentum. Large-scale flows affect small-scale convective driving. Missing either one introduces errors in both. Some of the most advanced solar simulations now running use grid resolutions that resolve features a few dozen miles across, while spanning volumes large enough to cover a significant fraction of the convective zone. These are remarkable technical achievements. But even at this resolution, they cannot simultaneously capture all the scales of motion that real solar convection involves. The turbulent cascade of energy from large to small, and the back reaction of small-scale turbulence on large-scale flows must be approximated through subgrid models, mathematical representations of physics too small to resolve directly. The subgrid models themselves introduce assumptions. Different research groups use different subgrid approaches. This is one reason why simulations from different groups can produce different large-scale convective behavior, even when using the same basic physics equations. The unresolved scales are handled differently, and those differences propagate into the resolved scales. Progress is real. Simulations from 2023 and 2024 have come closer than any previous generation to matching helioseismic observations of the solar interior, while also reproducing surface features like granules and differential rotation. Some of these newer simulations incorporate stronger rotational constraints and show large-scale convective flows more consistent with what observations suggest. The gap between simulation and measurement is narrowing, but a complete, physically self-consistent simulation of the entire convective zone at the precision needed to resolve the convective conundrum definitively is still years, possibly decades, away even with projected improvements in computing power. In the meantime, the mismatch points at a concept that some researchers think could explain multiple anomalies at once. Something happens at the bottom of the convective zone that current models treat as a clean boundary, but the real sun may be treating very differently. The textbook picture of the sun's interior draws a clean line between the radiative zone and the convective zone. Below the line, energy travels by radiation. Above it, energy travels by convection. The tachocline sits at this boundary, and for many years models treated it as a relatively sharp transition. Below is one regime, above is another. The physics on each side was developed more or less independently. Real fluids don't respect clean lines. When convective motions carry plasma downward toward the base of the convective zone, they don't stop abruptly at the boundary. They overshoot. A downward moving plume carries momentum. That momentum carries it past the nominal boundary and into the upper layers of the radiative zone below before it decelerates and turns back. This process is called convective overshoot, and it has significant consequences for everything that happens near the tachocline. The first consequence is mixing. Material from the convective zone gets partially mixed into the top of the radiative zone, and material from the radiative zone gets partially entrained upward into the convective zone. This exchange blurs the clean composition boundary that solar models draw at this depth. It means that heavy elements settling downward toward the core might be partially dredged back up, and light elements from the convective zone might be pushed deeper than a clean boundary model predicts. The solar abundance problem is affected by this. One of the proposed fixes for the mismatch between the revised surface composition and the helioseismic interior measurements involves adding extra mixing at the base of the convective zone. If overshoot is more vigorous than standard models assume, the composition profile through the interior would change enough to improve the helioseismic fit. This fix requires the overshoot to be in a specific range, vigorous enough to mix significantly, but not so extreme as to create other problems in the model. Whether the real overshoot actually sits in that range is not yet confirmed. The second consequence involves the magnetic field. The tachocline has long been thought to be where magnetic field is stored between solar cycles and where the shear amplifies it before the next cycle ramps up. If convective overshoot reaches into the upper tachocline, it stirs that stored field, potentially disrupting the ordered storage and amplification that dynamo models rely on. Getting the overshoot depth and intensity right is then not just a detail of the convective zone structure. It directly affects how the magnetic cycle builds and releases energy. Some researchers have proposed that the tachocline itself is partly maintained by the magnetic field, with the field acting as a kind of stiffener that limits how far the differential rotation penetrates downward and how much the boundary layer spreads. In this picture, the magnetic field and the rotation are in a feedback loop with the convective overshoot, each shaping the others in ways that make the boundary a dynamic, self-regulating zone rather than a passive line. If the overshoot is genuinely more complex than current models allow, then the solar abundance problem, the convective conundrum, the dynamo mystery, and the tachocline structure may all be connected symptoms of the same underestimated physics happening at this single hidden boundary deep inside the sunday. And what the sun reveals about this boundary won't just change solar physics. The sun's interior problems might seem like a niche concern, one star, one set of measurements, one cluster of unsolved puzzles, but every stellar model in astrophysics is calibrated against the sunday. Every prediction about how other stars evolve, how long they live, and what they produce is built on the foundation of solar physics. If that foundation has cracks, the entire structure built on top of it is affected. Consider how astronomers estimate the age of distant star clusters. They use stellar evolution models that predict how stars of different masses and compositions change over time. These models trace the evolution of a star from its birth on the main sequence, all the way to its eventual death, and they rely on the same basic physics that describes the sun's interior: the convective zone structure, the opacity, the composition profile, the overshoot at the boundary. All of these go into the models. Ages derived from star clusters are used to calibrate the age of the universe itself, to date the formation of galaxies, and to understand the history of chemical enrichment across cosmic time. If the sun's standard model is producing a convective zone that doesn't match reality, then the equivalent models for other stars carry the same systematic error, scaled for different masses and compositions. Stars slightly more massive than the sun have deeper convective zones. Stars slightly less massive have shallower ones. Some stars have convective cores instead of, or in addition to, convective envelopes. The errors propagate differently depending on the stellar type, but they propagate. The solar abundance problem has a specific parallel in this context. The sun's composition is used as a reference point for the composition of stars across the galaxy. When scientists measure the iron abundance of a distant star, they express it relative to the sun's iron abundance. If the sun's reference composition is uncertain enough to produce a significant mismatch in interior models, then the reference scale for stellar abundances everywhere carries that uncertainty. Asteroseismology, the same technique as helioseismology, but applied to other stars, is expanding rapidly. The Kepler and TESS space telescopes have detected stellar oscillations in thousands of stars, giving scientists the ability to probe interior structure in stars across a wide range of types and ages. Interpreting those oscillation signals correctly requires the same theoretical tools used for the sunday. Calibrating those tools against the sun and fixing the inconsistencies in the solar models is therefore not just a solar physics project. It is a prerequisite for reliable asteroseismic science across the entire galaxy. A better solar interior model would ripple outward into better stellar evolution models, better age estimates for star clusters, better understanding of how different stellar populations contribute to the chemical history of the galaxy, and better predictions for how stars of different types produce and distribute the elements that make up planets and, eventually, life. The Sun is close enough that scientists can measure it in extraordinary detail. Getting it right is both a scientific goal in its own right and the key that unlocks reliable models of every star too distant to probe directly, which is every star except one. The tools being developed to close the gap on the Sun's interior are impressive, and the next generation of them may finally break some of the logjams that have held the field back for 2 decades. The tools scientists use to study the Sun's interior are about to get significantly more powerful. A new generation of observatories, both on the ground and in space, is either already collecting data or coming online in the next few years. Each one pushes the boundaries of what helioseismology can resolve. On the ground, the Daniel K. Inouye Solar Telescope in Hawaii began science operations in 2022. It is the largest solar telescope in the world, with a primary mirror spanning more than 13 feet, giving it a resolution capable of imaging features on the Sun's surface as small as 18 miles across. For comparison, the granules that earlier telescopes could just barely resolve appear in Inouye images with crisp internal structure. This level of detail opens up helioseismic studies of the near-surface convective layers at a precision that wasn't achievable before. In space, the European Space Agency's Solar Orbiter was launched in 2020 and is now conducting science from an orbit that brings it closer to the Sun than any previous solar-focused spacecraft. At its closest approach, it passes inside the orbit of Mercury. From that vantage point, it can observe the solar poles directly, a perspective that Earth-based and near-Earth spacecraft can't achieve. The polar regions are where some of the most uncertain flows in the convective zone are located, including the high-latitude return flows of meridional circulation and the polar rotation rate that sets the differential rotation contrast. Solar Orbiter's polar observations are producing data that will constrain these flows at latitudes where measurement was previously very poor. NASA's Parker Solar Probe, launched in 2018, is on a mission profile that takes it progressively closer to the Sun over a series of orbital maneuvers using Venus flybys. At its closest passes, it skims through the outer corona just a few million miles from the solar surface, closer than any spacecraft before. It measures the solar wind, the magnetic field, and the plasma properties in the region where eruptions are launched and where the coronal heating problem plays out. Its data is already forcing revisions to models of the inner heliosphere, and as it gets closer, it is sampling regions that were entirely inaccessible before. On the computational side, several groups are developing next-generation helioseismic analysis pipelines, designed specifically to address the scale and geometry questions at the heart of the convective conundrum. These pipelines use machine learning tools trained on large solar simulation datasets to identify flow patterns in the observational data that traditional analysis methods might miss. Early results from these approaches are promising, suggesting that some of the signal attributed to noise in older analyses may contain real physical information about deep convective structures. The combination of better telescopes, better orbital coverage, closer spacecraft, and smarter analysis tools creates a situation where the field is genuinely positioned to make progress on some of the problems that have resisted solution for 2 decades. The convective conundrum, the solar abundance problem, the meridional circulation uncertainty, the tachocline overshoot question, all of them are being targeted simultaneously from multiple directions. Whether that progress will produce a clean resolution or reveal something deeper and stranger is an open question. But the history of solar science suggests that looking more carefully has a reliable track record of producing surprises. The Sun was born about 4.5 billion years ago from a collapsing cloud of gas and dust. It arrived on the main sequence, spinning significantly faster than it does today. Young stars in the same mass range as the Sun rotate several times faster, and the Sun's early rapid rotation shaped its interior in ways that may still be visible in the data today. When the sun was spinning fast, the Coriolis effect on convection was proportionally stronger. The suppression of large-scale convective cells by rotation was more intense. The tachocline shear was different. The differential rotation contrast between equator and poles may have been larger or smaller depending on how rotation and convection equilibrated at that early spin rate. And the magnetic dynamo running on all of these inputs produced a younger sun with far more intense magnetic activity than the relatively calm middle-aged star we see today. As the sun aged, it shed angular momentum through the solar wind. Charged particles streaming off the surface carry a tiny amount of spin with them, and over billions of years, this continuous loss slowed the sun's rotation to its current rate. That spin down was not uniform across the interior. The surface layers shed angular momentum first. The deep interior, insulated from direct contact with the solar wind, may have slowed more gradually. Some models suggest that the very deep radiative zone, below the tachocline, might still carry a memory of faster rotation from the sun's youth, rotating slightly faster than the convective zone above it in a way that creates subtle but potentially detectable signals. If this rotational fossil exists, helioseismology should in principle be able to detect it. Some researchers have looked for signs of it in the existing data. The results are inconclusive but intriguing. A faster rotating deep interior would affect the sound speed profile in a specific way, and the current heliosismic measurements leave enough room in the uncertainties to accommodate it. The composition of the solar interior also carries information about the sun's history. The distribution of helium between the core and the outer layers, the degree of settling of heavy elements toward the center, and the degree of mixing at the base of the convective zone all reflect processes that have operated over 4.5 billion years. Reconstructing that history from the current interior structure is a bit like reading the growth rings in a tree. Each ring records the conditions of a particular year. The interior of the sun records the conditions of its entire life. Getting that history right matters for more than just solar science. The sun's luminosity, the total energy it outputs, has changed over its lifetime, and the rate of that change affects how Earth's climate evolved. Models of Earth's early climate, particularly the puzzle of why early Earth was warm enough for liquid water, despite a sun that was about 30% dimmer than today, depend on knowing the sun's luminosity history precisely. The interior structure and the uncertain physics of the convective zone feeds directly into those luminosity estimates. The sun's past is written inside it, in the flows and compositions and rotation rates of its hidden layers. Reading that record fully requires solving the same problems that have occupied the field for the past 2 decades, and the implications extend far beyond the sun itself. There is a version of this story where the sun's interior problems are presented as a crisis. Models are wrong. Measurements disagree. The star we depend on for all life on Earth is doing things that science can't fully explain. That framing is dramatic, but it misses the actual significance. Science doesn't progress by having everything work perfectly. It progresses by finding where things don't work and asking why. The convective conundrum, the solar abundance problem, the meridional circulation uncertainty, the coronal heating mystery, the tachocline overshoot question, all of these are not signs that solar physics has failed. They are the active frontier of a field doing exactly what science is supposed to do, pushing measurements to the edge of what's resolvable, finding discrepancies, and refusing to dismiss them. The neutrino story is the model. For 3 decades, the solar neutrino problem sat there as an embarrassing gap between observation and theory. It could have been swept under the rug. It wasn't. Researchers kept measuring, kept refining, kept arguing, and eventually the gap turned out to be pointing at something fundamental about the nature of matter itself. Neutrino oscillation, a property of particles that rewrote the standard model of particle physics, was hiding inside that gap. The convective conundrum could resolve into something boring. better helioseismic techniques might find the missing convective signal. A recalibrated simulation might produce flows that match the observations without requiring any new physics. The solar abundance problem might resolve when better opacity tables become available. These would be satisfying outcomes. They would sharpen the model without requiring a revolution. Or the convective conundrum could resolve into something larger. The flows in the deep interior might be suppressed by a mechanism that current physics doesn't capture. The interaction between convection, rotation, and magnetic fields might involve a feedback that existing dynamo models are structurally unable to reproduce. The tachocline might be doing something at its boundary that requires rethinking how stellar interiors store and release magnetic energy. Either possibility is worth pursuing with full scientific seriousness. That is what the field is doing. Multiple independent research groups, observatories on the ground and in space, supercomputing centers on 3 continents, and the accumulated data from more than 4 decades of continuous solar observation are all being aimed at the same cluster of questions. The Sun is not unique in having unresolved interior questions. Every star in the sky has an interior that scientists model but cannot directly observe. What makes the Sun special is that it's close enough to test those models at a precision unavailable for any other star. Every inconsistency found in the solar data is a precision test that other stars can never provide. The discrepancies are not embarrassments. They are the highest resolution view of stellar physics that the universe has made available to us. Getting the Sun right doesn't just mean understanding one star. It means building the most rigorous possible foundation for understanding all of them. And the implications of that reach far beyond physics. Of all the stars in the observable universe, the one scientists should know best is the Sunday. It sits 93 million miles away, close enough to fill an entire hemisphere of sky at sunrise and sunset, close enough to damage your eyes if you look directly at it for more than a moment. Humans have been watching it for thousands of years. Modern science has been measuring it with precision instruments for more than a century. Space telescopes have watched it continuously, without interruption, for over a decade, and it is still sending back data that the best models in the world cannot fully explain. That is not a failure of science. It is science working exactly as it should, at the ragged edge of what is known, where every new measurement has a chance to reveal something that changes the picture. The Sun is close enough to probe in extraordinary detail, and that detail is precisely what exposes the gaps. A distant star reveals only its surface. The Sun reveals its interior, and the interior, it turns out, is far more complicated than the textbook diagram suggests. The convective conundrum tells us that the engine moving heat through the outer third of the Sun is quieter, more rotationally organized, or more geometrically unusual than every standard simulation predicted. The solar abundance problem tells us that the most basic question, what the Sun is made of, is still not settled precisely enough to anchor the interior model. The meridional circulation uncertainty tells us that the clock running the 11-year sunspot cycle is ticking at a rate we can't measure cleanly. The tachocline mystery tells us that the single most magnetically important layer in the star is doing something at its boundary that current physics doesn't fully describe. Each of these problems is being actively worked on by scientists who have dedicated careers to pushing the measurements further and the models deeper. Progress is happening. The data is getting better. The simulations are getting more realistic. The gap between observation and model is narrowing, even when it's not yet closed. But the deeper lesson is about what it means to study something as familiar as the Sunday. Most people look at the Sun and see certainty, warmth, light, stability, the star that never fails to rise. Science looks at the same object and sees an open question, a set of measurements that don't quite line up, a model that works well enough to be useful, but not well enough to be trusted completely. That tension between the everyday reliability of the Sun and the scientific uncertainty about how it actually works is the real story. The Sun has already forced physics to discover neutrino oscillation. It has revealed the coronal heating paradox, which remains incompletely explained after 80 years. It has produced a convective conundrum that has resisted resolution for more than a decade, and it rises every morning, unchanged to the eye, pouring out the same light and heat, carrying signals from its hidden interior that scientists are still learning to read. The closest star, the most studied object in the sky, the foundation of all life on Earth, still full of questions, and still, every few years, sending back data that makes the physicists start over.